So, okay, good evening everyone. So I hope everybody has submitted their project submissions, their groups. I mean, if you are in a group, then ensure that somebody in your group has submitted. Okay, so yeah.
There's something going on with the lights. They're on. Lights are on.
Okay, there is a plus sign. I don't know how to get rid of that. So we will navigate around that. So few logistics. Firstly, assignment 1 will be graded very soon by the TA. So if you hopefully she'll upload the grades and you can contact her for any clarifications. And project reports will be assessed after that. Assignment 2 is out today, so have a look. One or two questions are, I think one question at least will not be covered till today, so we'll have to wait till next week so that there is enough content for you to approach that question. It is towards the end, and you have 3 effective weeks excluding the spring break, so you really have a long time for that assignment. So it is considerably less time taking than the first assignment. That's my expectation. So, okay, so today we will look at the second part of the graphical models topic. So today we're going to look at something called inference. So I'll again remotivate why we are studying graphical models, and then look at what we kind of went through last time, which is directed graphical models. Today we're going to look at a different type of graphical models called undirected graphical models, and then get to the meat of the problem, which is inference. Okay. So just a recap of what we did in this course. In the first 6 lectures, we were looking at deep learning techniques for unstructured data. So predominantly vision, computer vision encompasses images and videos and so on. And we also looked at text models like RNNs and word embeddings. We will see something called control, which is essentially related to decision making or various other names in the third part of this course, which is called reinforcement learning. So for this part, the second part of this course, for structured data, we are studying graphical models, and you'll come to realize that graphical models are a very general framework which will encompass many models that you've seen before, like Gaussian mixture models or Kalman filtering if you're from engineering background. Even your cell phones use actually graphical models, some techniques related to inference and graphical models to actually decode messages actually. And there's something called hidden Markov models, which you might have also seen in text processing or in speech processing. So there are many successful applications, and in fact, even you can think of naive-bayes method and conditional random fields. So there are some techniques that you might have come across as at least words before. So these are also special cases of what we are studying. So it's really a generalist framework. Okay. So what are graphical models actually good at? There are 3 aspects to this problem. One is representation. The reason why we want to use graphs to represent joint distributions or density functions is because graphs help us capture which random variable is interacting with which other random variable. They also let us capture one interesting property, which is the conditional independence property. Which random variables are independent of which other random variables if I have observed some parts of my distribution, right? And so that was what we spent most of our time on last week. in addition to reviewing some concepts in probability and graphs, right? So we focused on conditional independence properties that can be captured from directed graphical models last time. And in general, graphs are also useful for visualization. So today we're going to spend on the second big chunk of the use of graphical models. Once I can represent a joint distribution using a graphical model, I can do something called inference, and we'll get to what inference is pretty soon. Inference is the problem of computing functions of joint distributions. So for example, expectation is a function of a joint distribution, right? To compute the expectation, you need to do a summation over x times probability of x, for example, or integration of x times probability of x. So it's a function of your joint distribution. Similarly, there are other functions like conditional distributions, marginals, and so on. We'll learn how to compute them efficiently, and we'll get to why a naive computation is very, very inefficient once you get to 10 random variables even. Okay. And the third part, which we'll cover in the next lecture, is going to be how we learn the parameters of the joint distribution. So we are going we are going about this topic in an inverted way than what you see in let's say a data mining technique, or even in the first part of this course. We are not learning the model first and then doing computations on it. We are first trying to understand what's the use of this model, because it captures conditional independence. If I had the model, what can I do, which is inference, and then towards the end we'll actually get to how do I get the parameters of the model. Okay, so that will actually tie to something that you may or may not have come across called maximum likelihood estimation. Okay, so so as I said, we looked at representation last time. So how does a directed graphical model look like, and what does it encode? And today we're going to look at undirected graphical model. We know that it encodes conditional independences, and we'll see that again. Today again we look at computing specifically marginal distributions and conditional distributions efficiently. And next time we'll look at estimation of the parameters of the model. Okay. Any questions before I even go further? The big picture should be clear why we are studying this set of models for structured data. Structured data implies numerical, categorical, ordinal, all sorts of the regular things that you've seen when you model variables as random variables and assume distributions, let's say, like Gaussian or multinomial or things like that. Okay, so let's look at directed graphical models. Okay, so given a bunch of random variables drawn from a distribution P, so distribution P is the joint distribution P that I'm talking about. Okay. And a directed acyclic graph G, we say that the set of random variables respects G, or equivalently the distribution respects G, if the joint distribution, which is the same P here, just expanded in terms of, so this is x1, so expanded, is in the product form, where it's a product over every random variable in the set, conditional on its parents. So last time, if you remember, for a directed acyclic graph, we know what the parents of a node were. So that's what this means. So this joint distribution decomposes as a product of these factors or conditional distributions, which are probability of xi given the parents of xi. Okay. So this is a product of n terms, because there are n random variables here. And one example that we kind of rushed through last time was this particular Bayesian network. So a directed probabilistic graphical model is also called a Bayesian network. So you might have come across BayesNet or something. So this is what it is. So here, this graph is actually having 5 nodes. The nodes are actually explicitly given the metadata of difficulty, intelligence, grade, SAT, and letter. So it's a stylized example. So there are 5 random variables. So there will be 5 factors. Each factor, so there will be 5 factors here in the joint distribution, and each factor is explicitly written in this last equation here. So since so I guess they're using D to represent the node difficulty. So since difficulty doesn't depend on anything, it's probability of D, right? Because it's conditioned on the parents of D, and parents of D is an empty set, which is you can write condition on phi or something. And same thing with probability of intelligence. And next, grade depends on, so the grade node depends on the two parents that it has. So grade condition on I and D. Okay. Same thing with SAT condition on intelligence, and then probability of letter given the grade. Okay. So that's the graph. Okay. There are directed edges here. So this graph and this joint distribution are related, right? So that's the example student network. Now, just looking at the graph, now if you can forget the joint distribution, just look at the graph. We can talk about independences that we can read off from this graph. What do I mean by that? So given a graphical model, we can determine if two sets of random variables or two random variables, it doesn't have to be sets, are conditionally independent or not. So for example, in this 3-node directed graph, okay, this 3-node directed graph will correspond to some joint distribution, which we are not concerned in on this slide. What we want to say is that if there is a 3-node graph with directed edges like this, then the nodes A and B are actually conditionally independent given C. Okay. Same thing with this other 3-node graphical directed probabilistic graphical model, where A and B are again conditionally independent of C. But if the nodes go to the node which is being conditioned on, then A and B are not independent given C. Okay. In the sense that you can't read off that A and B are independent if C is conditioned on, as in C is observed or something like that. Okay. So this can be, for example, a part of a huge graphical model, and you can just read off that different subsets of random variables in the graph are conditionally independent of each other. And that was the concept that we got to towards the end of the last lecture, which was this notion of d-separation. Okay. So here there are only 3 variants possible in 3-node graph, right? Either, for example, here A can go to C and then go to B, or you can have the opposite direction, B can go to C and then to A. But there are essentially 3 sets of graphs that you can have with 2 edges. Okay. But for really larger graphs, you need a general notion, and that's why we're going to study something called d-separation. And to define d-separation property, d-separation just stands for directed separation in the graph. So it's still a graphical concept. To get there, we're going to define the concept of a path being blocked. So a path is also a graph concept, right? We kind of reviewed that last time. A path is just a sequence of vertices from a starting vertex to an ending vertex, such that every pair of vertex has an edge between them in that sequence. So a path between 2 vertices is going to be blocked with respect to C. Okay. So what is the C here? So again, if you think of a general graph, you can pick any node and call it a C, or you can pick a subset of nodes and call it a C set. Okay. So C can be a set or a node itself. So whatever eases your understanding, you can think of it that way. So a path is blocked between 2 vertices with respect to C if it passes through a node. B, such that let's focus on the first condition. V belongs to the C. Okay, and the arrows are head to tail or tail to tail. Okay, so the arrows directions that we saw, if it is tail to tail or head to tail, and that node is in C, then that path between the 2 vertices is blocked. Okay, pick any path between 2 vertices. If there is a node on that path which belongs to the set C, and it's connected in a head to tail or a tail to tail way, then that path is blocked. That's all it means. Okay, and similarly, there's another condition which is related to the head-to-head situation of a node B. If a node B exists, which is in a head-to-head condition, but it is not in C, and its descendants are also not in C, then the path is blocked. So it's a slightly non-intuitive condition, but it's just you can kind of mechanically check this. Okay. So path. So we just understood what is meant by a path being blocked. So d-separation is just that a set of vertices A and a set of vertices B are d-separated by a set of vertices C, okay, or it could be just individual vertices themselves, if all paths from the vertices in A to vertices in B are blocked with respect to C. So let's say A has 2 vertices, B has 3 vertices, then potentially there could be 2 times 3 paths, right? So if all paths are blocked, then A and B are d-separated. Okay. And if A and B are d-separated, then they are conditionally independent given C. That's it. So it's just a generalization of a thing that we saw 2 slides ago. So an example that we were looking at last time, I guess this is the second example, was let's say C is x3. So this is the directed graphical model, x1, x2, x3, x4, x5. Let's say these are the directed edges. Okay. Let's say we pick C to be this node and A to be this node. So I don't know if you can see the color difference, but A is this node, and then let's say B is these 2 nodes. Okay. Some sets of nodes. Now we can check whether the set A is conditionally independent of the set of vertices B given this node C. In the sense, given the node C means you have observed C. That's the interpretation. And we can check that by checking the d-separation of all pairs of vertices, xi and xj, where I is in let's say set A and j is in set B. So B includes 2 and 4, right? And so we can actually check. So let's say 1 and 2. Okay, 1 and 2 are not blocked by C. Why is that? Because it follows from the second condition that we saw, right? And second one is 1 and 4, 1 and 4. This is a I guess a head to tail relationship, and so it is blocked by C, right? So yeah.
When there are large number of nodes, are we going to visually just check for each node head to head?
No. So this can be made computational, but this is to read off something. Let's say you had a 10 node graph. I mean, you visualize that graph. You can even not even a 10 node. Even if you have 1,000 node graph, you can plot a graph, right? You can also kind of bunch multiple nodes together and call that huge set A and huge set B, something like this, right? You can just check whether you firstly have to isolate the nodes that you want to understand conditional independence behavior of, right? For example, in the student network, or a large network, you want to know whether grade is independent of getting a SAT number, high or low, given intelligence. Things like that. That's what you want to see. That's the type of patterns that you want to detect in your data set, right? So you have this type of a graph which may have more number of variables, but you will have semantic meaning to them, and you want to understand the conditional independence between them. If I've already observed something, then the probability of something else happening should not be influenced by another node, right? So we check for all paths, and then because one of them is not blocked, these are not deep separated, so we cannot say that they are conditionally independent. Okay, that's what we covered last time. So any questions? Okay, so today we'll look at undirected graphical models now, which are actually simpler than what we saw last time, and then we'll directly jump to inference. Okay, so undirected graphical models. So these are also called Markov random fields or Markov networks. So these are terms that you may, if somebody says let's model it as a Markov random field, then this is what they are talking about, undirected probabilistic graphical model. And if somebody says let's model it as a Bayesian network, they're talking about the first part that we saw. Okay, so the only difference is that we don't have edge directions, and these diagrams again help us kind of visualize probability distributions and capture certain other conditional independence properties. So directed probabilistic graphical models capture certain conditional independence properties. Undirected ones also capture conditional independence properties. There is slight difference between them. So we'll kind of see what are the differences in a few slides. Okay. Directed graphical models are used in a lot of machine learning and statistics. So as I said, naive Bayes method, hidden Markov model, even Gaussian regression, Gaussian mixture model. All those are parts. All those are just special versions of the framework that we are studying. Undirected graphical models have been used in computer vision mostly. So all the image processing stuff that you saw in the first 4 lectures, before deep learning kind of be the state of the art, graphical models are a big way to model the structure in images. Okay, to for example, segment images, do foreground versus background subtraction, a lot of different image processing tasks. Okay. So one key difference between directed probabilistic graphical model and undirected probabilistic graphical model is that directed models have factors of the distribution, which was the product form that we saw. Those factors were actually conditional distributions, right? Probability of xi given parents of xi. That's actually p of xi given parents of xi is actually a conditional distribution. Okay. In undirected graphical models, the factors, the terms which get multiplied to kind of represent the joint distribution, they're also called potential, and they need not be a distribution. They need not be anything. They're just functions. Okay. For example, let's say we are writing the joint distribution for 3 random variables. So let's say a particular instantiation of those variables. Then probability of a, b, c can be written as let's say some normalizing constant times some function of AB and some function of BC. Okay. Now, so these functions need not represent joint distributions or joint distributions or a smaller set of variables or conditional distributions or anything. Okay. And Z is just a normalization constant to ensure that this is actually a valid probability distribution function. Okay. So because if you sum over all the realizations or all the configurations of these 3 random variables, it should sum to 1, right? And the Z is also pretty famous. It's called the partition function, and it's very, very hard to compute, and lots of PhDs and lots of work in physics and computer vision to work on estimating this. Okay. So what is the notion of a potential? So this P function of a single variable or multiple variable is just a non-negative function, or in this case multiple variable is just a non-negative function. Okay, and this is what we saw. So P of ABC was this, and the graph that I'm going to draw for ABC, since there are 2 such functions, I'm going to draw 2 edges. Okay, in this 3-node graph, but that's not the way I'm going to draw graphs, undirected graphs. So we'll get to how to generalize that. Okay, so this would be the factored form of the joint distribution function, and this would be a candidate undirected graph for this joint distribution. Okay, I'm just proposing 2 candidates. So what exactly is the joint distribution that I care about? So let's say for D random variables, I'm going to define the graphical model as a product of the potential over the cliques of a graph, cliques of the graph G. Okay. Do you remember what cliques were from last lecture's review? So cliques are just subgraphs of a graph where every node is connected to every other node in that subgraph. Okay. So for example, we have examples. So even in this example, for example, this is a clique, because if you think of this subgraph A comma B, then it's a very simple clique because every node here connects to every other node because there's only one other node, right? Same thing on this side, that's a clique. So what we are saying is that an undirected probabilistic graphical model is represented as this, where the joint distribution is decomposed into a product of functions, so where those functions are functions of elements of the clique, as in nodes corresponding to the clique. Okay, and Z again is a normalizing constant. When you sum over all configurations of all realizations of your random variables, then it should sum. It should be such that this term sums to 1, right? So when cliques are of size 2, the graphical model is called a pairwise graphical model, and when all potentials are strictly positive, it's called a Gibbs distribution. But we don't care about. Let's say these are minor points. So the main thing is graphical model is essentially undirected graphical model is essentially a product of functions where functions are defined over cliques. Okay. So for example, let's look at this graph, which has 3 nodes and 3 edges. I'm just gonna define functions over cliques, right? So I just see this graph. Okay, this graph I can think of it as having one clique with 3 nodes, or I can think of it as having 3 additional cliques, right? So I'm just going to take the latter view by just choice. I could have chosen the first view as well. So because I have 3 cliques, I'll define 3 functions. So function over A and B, function over B and C, and function over A and C. Okay. And what are these functions? For every possible values of A, B, and C. For example, in the first one, these are binary random variables. So if A takes a value 0, B takes a value 0, then I'm gonna output the function output as 10. Okay. So that's what these tables represent. These tables represent all is completely represent this function, right? So that I can do for all the 3 functions, and then I'm going to define the joint probability to be the product of these 3 functions for every realization, where z is again the normalizing constant. Okay. So is this definition clear of functions, the product of the functions being the way the joint probability splits and so on?
How did you define Z?
Z is just supposed to ensure that because these numbers are not even between 0 and 1, when I multiply these numbers are going to go greater than 1, right? So I need essentially Z is supposed to be such that when I sum over all A, B, and C values, so there are eight configurations, right? A, B, and C being 0, 0, 0, all the way to A, B, and C being 1, 1, 1. So all the 8 configurations, if I sum over that, that should be equal to 1. So Z should take care of that. That's all. So that's what is happening, right? So A, B, and C over all their potential values, all their values, which is 0 or 1. The raised to 3 is just saying A takes a value 0 and 1, B takes a value 0 and 1, C takes a value 0 and 1. The sum over all these configurations of the numerator, this is essentially the numerator, is some value. And when I put that 1 by Z value there, then I know that this is a valid joint distribution. Right?
The output with 10 is random.
What is random?
10, like A0 and B0.
No, it's not a random, it's a function, right? It's a deterministic function. There's no randomness. So once we define joint distribution object is not a random quantity, right? You can sample from a joint distribution and you can define a random variable which and in fact this joint distribution over 3 random variables, so you can realize the random variables from this joint distribution, but this is a fixed quantity and these are some fixed numbers which define the joint distribution, right? Any questions? Okay, let's look at a couple of concepts. So first thing is marginalization on this undirected graphical model. Okay, so marginalization is essentially summing over all the irrelevant random variables. Okay, so for example, if I have a graph or even a bigger graph where these could be sets, and if I marginalize over B, all I mean is that I sum over B, all the realizations of B. Okay, then it makes A and B graphically dependent in the sense if I marginalize over B, I get essentially something like this. Okay, so marginalization of B is just captured here. For example, if I had the joint distribution and I want to get rid of B, I want just the this would be called a marginal, although it has to still do random variables. This marginal is obtained by just summing over all realizations of B of the joint distribution. So I get rid of B and I get something like this. So this can be represented as this, right? Because there's one factor here where this phi 3 was not defined earlier. I think. Yeah, it's some other function. So marginalization should be very clear in the sense it's just getting rid of variables by summing over all their realizations. Okay. And graphically, what it means is that if I get rid of that variable, I may have factors which will include the remaining guys, right? Remaining random variables. And so, however they look like, I can just define a appropriate graph, right? Because we were defining graphs as corresponding to functions of corresponding. If there's a function of a clique, then we'll just make a clique there, right? So here it's a single edge clique, so clique with two vertices, so we have that function, right?
Are you saying each edge corresponds to a potential?
In this version, yeah. I mean, here there was no. I did not even write the. Here the graphical model. If this is a graphical model, then I'll have two factors, okay. And I marginalize it over. I just have one factor with two guys left. So I'm just drawing this as a graphical model. So that's marginalization, but that's not very interesting. What is interesting is conditional independence. Okay. So in undirected graphical models, conditional independence concept is quite a lot simpler, and it is as follows: conditioning on B makes A and C independent. In the sense, probability of A comma C given B is probability of A given B times probability of C given B. That's the definition for conditional independence. And if the graph looks like this, and I condition on B, then A and C are independent. That's what it means. Okay. So in the undirected graphical models, it was more nuanced because there were edges present. If we had a V structure, it was not. We could not claim that A and C were conditionally independent given the central node. But in this case, if there is a node in between, things get conditionally independent easily. And we'll actually go over this in a couple of more slides if it's not clear. So there are two ways to kind of formalize this conditional independence notion, and first is called the global Markov property, and the second is called the local Markov property. So what does global Markov property mean? Let's say we have two sets of nodes. Okay, so let's say the first set is A and the second set is B, and they are conditionally independent given a third set C if all nodes in A and B are connected through nodes in C. Okay, it's a very intuitive concept. Let's say you have a huge undirected graphical model, okay, and you call one set of nodes A, one other set of nodes B, and remaining set of nodes C. Then the two sets A and B are conditionally independent given C if all nodes in A and B are connected through the nodes in C. In the sense, let's say you pick one node from A, one node from B, pick a path. If the path has to pass through C, then they are conditionally independent. Okay, that has to happen for every pair of nodes. Yeah.
Connected only through nodes in C, or if connected through nodes in C?
No, only all nodes in A and B are connected through nodes in C. So they cannot be connected outside.
Anywhere else. Only through nodes in C.
Yeah. Yeah, I mean it's clear, right? I mean if they are connected directly, then we can't call them conditionally independent. So, okay, the next version of the same thing actually, but from a local perspective is as follows. Conditioning on the neighbors of X makes X independent of the rest of the graph. Okay, so in other words, probability of Xi given let's say a bunch of the remaining random variables in my set of random variables, 1 to D, is just going to be probability of Xi given the neighborhood of Xi. We defined neighborhood even in the last class review for graphs. So these are the conditional independence properties that you can read off from a given undirected graphical model. Okay, so let's go through an example. So in this graphical model, okay, as a consequence of global Markov property, you can see that x1, x2, and x3 are conditionally independent of 5, 6, and 7 given x4, right? So I'm just calling this set to be A, this set to be B, and this set to be C. And for the same graph, I could apply the same global independence property elsewhere, but if you look at it from a local perspective, so if I want to apply the local Markov property, then I can say that x4 is independent of x1 and x7 given its neighborhood, which is 2, 3, 5, and 6. Okay. And similarly for x1 is independent of all these 4 nodes given 2 and 3, right? Because if I make this is the neighborhood, so given the neighborhood, this guy is independent of everybody else. Okay. So clearly, the undirected graph specifies a set of conditional independent statements. That's what we read off from the graph, and we can also write a joint distribution using the graph. Right? We saw that with the 3-node graph, we could write a joint distribution. With this 3-node graph, we wrote a joint distribution which had 3 factors, right, for every edge, right? But we could also consider a joint distribution which was, because we have a clique here which has 3 nodes itself, we could have written a single factor, right? So okay, for the graph that we are seeing in the previous couple of slides, for example, this graph, if we focus only on the maximal cliques, so maximal clique, do you remember what is called a maximal clique? Maximal clique is a clique where if you add one more node from the rest of the graph, it stops being a clique. Okay, so the subgraph is kind of maximal in that sense. Okay, so if I look at this graphical model, okay, this graph, this undirected graph, I can, if I only want to focus on writing this as a function of, from this I want to write the joint distribution using just the maximal cliques, functions over maximal cliques, then this is one, actually maximal cliques are like, actually this and this, right? Oh no, these are not cliques, sorry. Okay, so 1, 2, and 3, and 3, 4, and 2, those are the cliques. Similarly on that side, 4, 5, 6, and 5, 6, 7, those are the maximal cliques. So I'll write 4 factors. Okay. If I focused on writing it only as a function of maximal cliques. Okay. But we could also written, from the graph, if I wanted to write a joint distribution, I could have written it in some other way, right? I could have just chosen, for example, all the 2 cliques. So I could have written 1, 2, 3, 4, 5, 10 such factors. And I could have written other versions, right? For example, 2 factors here, but remaining are maximum cliques. So a lot of variants are there. I could have done that. So there is no uniqueness in reading from going from an undirected graph to a joint distribution. Remember, contrast this with the case of directed graphical models. In directed graphical models, every factor was actually a conditional distribution, which was probability of xi given parents of xi, and so there would be a factor for every node. Right? Here, there's a factor or whatever term for every clique, and so they can vary. Right? So the example that I was drawing on the board was if you have this graph, the joint distribution can be a single factor, or the joint distribution can be with 3 factors. Okay. To kind of get rid of this ambiguity, we define a slight extension which is called factor graphs. Okay. So what are factor graphs? So we're going to try to create a square node for each factor. A factor is the term in the joint distribution, right? So we'll create a square node for each factor and then change the graph in this way. So let's say if this was the original undirected graph, I'm going to create a square node, okay, and join it to all the random variables which are defined by that factor. So in this case, from this graph, because the joint distribution I wanted to represent it this way, I'm going to actually create a different graph, which is this. Okay. Now there is no ambiguity. By looking at this graph, I know that there's one factor, and that factor involves A, B, and C. So that's what I've written there, right? So more formally, for a function, of let's say d arguments. Okay, the factor graph has a square node for each of the. So here I'm saying it for a function, but you can think of it as a joint distribution function. The factor graph has a square node for each factor. So the joint distribution function is a product of factors, right? So there will be a square node for each factor and a circular variable node for each of the variable Vj. So the variable nodes are the same as before. I'm just introducing square factor nodes, which are gonna correspond to the factors in the joint distributions expression, right? And factor graphs, as we will see, will allow us to define inference algorithms, which is the content of this lecture, for both directed probabilistic graphical models and the undirected probabilistic graphical models. And they are just a richer way to represent the joint distribution, slightly richer way. Okay. For reading of conditional independencies, you may want to care about not the factor graphs but the original directed or undirected graphs. But for the purpose of inference, we'll look at factor graph to kind of ease our thinking of how the inference happens. Okay. So, for example, just to reiterate the point, there are two factor graphs here for the same Markov network or the same undirected probabilistic graphical model. So, for example, in this factor graph, we can read off that there is one clique, one large clique. So there's only one factor in the joint distribution expression. And here in this factor graph, we know that there is 1, 2, 3, 4, 5, 6 factors in the joint distribution expression. Okay. So couple of things. So first, let's look at an example. So which distribution does the following graph correspond to? We'll use f or phi to denote factors. So that's just without loss of generality, and we'll use lowercase to minimize notation clutter because anyway we are these are functions. Joint distribution is just a function of every realization. So when you write p of small a comma small b comma small c, it's implied that it's a function which is, for example, if a, b, and c are taking 2 values each, then it's a function which has 8 which maps 8 configurations to corresponding numbers, right? So it's just a function. So we can use small case letters. So what does which distribution does this graph correspond to? So first of all, how many factors are there? Okay. Is it clear which distribution this corresponds to?
How are FA and FB?
You can have two terms. It's not different. In this case, it's actually they've just written it with the same random variables. So I guess that way it's not a valid relation to the undirected probabilistic graphical model, but we are just trying to read off from a factor graph what the representation of the joint distribution would be. Okay.
But if it was let's say it was a directed graph, in that case this would exist, right? So
no, in a directed graph you will not have this. There will be one factor per node. So in a directed graph you will have potentially 3 factors. Okay. So actually, just it's a very simple thing. So you have 4 factors. So I'll just write 4 expressions, and whichever variables they're connected to, they are the arguments of those factors. That's all. Nothing much. I'm just trying to read off from a factor graph what the joint distribution is. And you can also go the other way. So let's say I have factors which look like this. Okay. First of all, you should think, okay, what is this notation? I was thinking factors were functions, right? So what does this mean? So instead of writing the joint probability, let's say in the directed graphical model case, directed probabilistic graphical model case, I had factors which are conditional distributions, right? So if I had a directed graphical model for x1, x2, and x3, and if I had 3 factors which look like this, then how would the directed graph look like? Yeah, so x3. Yeah, but how? What is the direction?
x1, x2 parent x.
Yeah. So this is how it would look like. So you don't really need a factor graph here. But if you now think of those three, so for this graph we know exactly what the factorization of the joint distribution looks like. But if you think of those three terms of the joint distribution to be functions now, because the conditional distribution is a function of three variables, right? Probability of A given B comma C is a function of A, B, and C, right? It needs three arguments to tell you what the probability is, right? So yeah, actually I could have used comma, but I kind of wanted to allude that it was a directed graphical model. I mean, it has a connection to a directed graphical model. So the factor graph is just this. You have three factors. So I'll just put three blocks. Two of the factors just have one random variable each, right? So there's one edge for two of the factors, one edge here, one edge here. But the factor in between is a function of three arguments. So there are three nodes connecting FC, right? That's the factor graph.
So are we saying that first the FC thing is x1, x2, x3?
It is, right? Conditional distribution is a function of three random variables. Is a function of. So in this case, the conditional distribution is a function of all its arguments. Although something like this, right? Probability of A is equal to A given B is equal to B and C is equal to C. You want to define this. It's still a function of, you still need, let's say A, B, and C are binary random variables. You still need 8 inputs to tell you what the outputs are. Basically, for every it's basically like for every pair you have 2 numbers. So for 4 pairs you have 8 numbers. So what I'm saying is this is like a function of A, B, and C. Right? Is this kind of trivial or is it confusing? So in fact, here I was alluding to a directed probabilistic graphical model, but in this slide I'm explicitly stating that it's a redundant activity, because if you have this graph, we can kind of know what they're exactly the number of factors, which is equal to the number of nodes, and we don't really have to explicitly write the factor nodes. But if we write the factor nodes, we can kind of ignore the directions because I mean, we'll lose information, but we'll have functions of the random variables involved. But we can do inference, as we'll see later, without knowing the directions. Okay. So, kind of finishing up on the representation part. So we saw 2 types of graphical models, directed and undirected. So we saw how to read conditional independence properties from just looking at graphs. I mean, we only looked at really small graphs. But you can imagine if I had a 100-node graph or a 1,000-node graph, the properties of d-separation and the global and the local Markov properties help you to quickly kind of eyeball which sets of random variables are conditionally independent of each other. Okay, and that you cannot do if you just have a joint distribution, huge joint distribution. Okay, but there are a few limitations. One of the key limitations is that you cannot represent all conditional independences of a given joint distribution using either of the models. For example, we cannot draw a directed probabilistic graphical model for this distribution in the sense, let's say we have a distribution with these conditional independence properties. Okay, then I cannot draw a directed probabilistic graphical model to represent these conditional independences. Okay. And we can verify that later. And similarly, for example, we cannot represent the following conditional independence and conditional dependence properties using an undirected probabilistic graphical model. And for some of you might identify this as precisely the head-to-head structure or the V structure, right? Remember, C had 2 C had 2 incoming nodes, so 2 parents. So there you couldn't a condition on, let's say, the not C. In this case, condition on, let's say, one of the nodes, the parents are not conditionally independent. Okay, that's what we saw for. We could model it using a directed probabilistic graphical model, but we cannot model it using an undirected graphical model, and we'll not do this because it's a slight tangent. We are happy that some graphs represent some distributions, and we'll go forward with that. But you should be aware that not all conditional independence properties that you want to impose can be represented as graphs. I mean, in either of the maybe if you can't represent these independences in this version, you can try using an undirected to represent those independences, and you can actually. It's very simple. Okay, in this case, it's just a ring with 4 nodes. In the sense, it's just if you want to represent the first one as a undirected graphical model, it's just A, B, C, D. So this is that undirected graph which represents those 2 conditional independence, right? Because if I condition on BD, A and C are independent because of the Markov property, global Markov property, and similarly condition on AC, BD are independent. That's that property. But what I'm saying is that the directed graph will not be able to capture those 2 independences. That's all. So any question with respect to the representation? Okay. So now we're going to look at inference, and so what I mean, I've been repeating, alluding to inference multiple times. So what exactly do we mean by inference? We'll again revisit that. So let x bar be a bunch of d random variables. So let x bar be a random vector, and let its domain be script x. Okay, where each random variable itself will have some values that it takes. So let's represent that as script I. And inference is all about given this joint distribution over the random variables, we want to compute functions of it. So what are those functions? For example, I know I may be interested in finding the mode. Okay, mode is just going to be that particular configuration which has the highest probability on my joint distribution, right? The second version is mean. I want to compute mean, and mean's definition is quite clear. Okay, let's say it's a scalar valued function of a bunch of random variables. Then you need to sum over all configurations, the g of that random variable, that realization vector times the probability of that realization vector, right? So what is what is a marginal computation? It's going to be, for example, just computing a marginal can be just max over all the random variables which are irrelevant, and for example taking the argmax over the random variable which is relevant. Okay, I mean this is like computing a mode of just a marginal. So if you forget the argmax part, then if you just focus on the inside, then this is just marginalizing over all irrelevant random variables, right? That's called a marginal. Yes. And a conditional is, as you've already seen, if I want to condition on all other random variables, then this could be a possible computation, right? I know all the values of the other random variables. Tell me the conditional distribution of my current random variable of interest. That's one computation. Okay, and this need not be for single random variables. I mean, as we were seeing last time, it could be conditional probability of xi, xj, xk condition on everything else. That is also a computation that I may be interested in. And we'll look at 3 key techniques. Actually, we'll spend most of the time on the second one. So the 3 techniques are called variable elimination, belief propagation, and sampling based methods, which are basically based on Markov chain Monte Carlo methods. Okay, and there are many other methods. We will not go into them. Okay, let's start with some more setting up of this process. So we have two different graphical model families, right? Directed and undirected. So as we will see, the inference methods that I'm going to discuss, which is in variable elimination, belief propagation, or Markov chain Monte Carlo methods, they can be used for both types of graphs. And for convenience, what we'll do is we'll construct an undirected graph from a directed graph and discuss inference on undirected graph in general. Okay. So if we have a directed graph, we're going to convert it into an undirected graph. Okay. So how do I do that? For each factor in the directed graph, I'll call it a potential, okay, or a factor. So the factors that I already had in my graph, I'll just call it potential. But in terms of representing the graph, because already I had a factorized version of the joint distribution, then that's fine. I have n factors. That's okay. All I'm going to do is, and I know that if there was a factor in a directed probabilistic graphical model is of the form probability of xi given parents of xi, right? Now, if I want to change it to call it as a general factor or general potential, then I have a function which is a function of the xi as well as the parents of xi. That's all. Okay, nothing has changed. So in terms of the product form, we are fine. But in terms of the graph itself, there is a process called moralization, which just means that if you have, if a node has parents, then you add an edge to the parents, okay, and that's it, and you get rid of all the directions. So for every node, if the parents are not connected, just connect them and ignore the directions. Okay. Of course, this process is just so that we can look at inference algorithms in a unified way. If you do this, information is lost clearly, right? Because this was condition on. Okay, information is lost. We are not gonna go into the detail. Okay. If information is not lost, I mean there may be additional conditional dependencies which may or may not be captured. What I'm saying is that there is no equivalence of transforming a directed graph to an undirected graph. We just saw an example of one graph being representable in undirected version but not representable in directed version. So they are not equivalent. But for the purposes of inference, we're gonna focus on undirected ones. But know that the directed ones can also be inferences on directed graphical models can also be performed the same way, unless I explicitly know that it is not. The three algorithms or three frameworks that we're going to look at today are applicable to both sets of graphical models. So what is variable elimination? Variable elimination is actually a very, very straightforward algorithm, so it should be easy. So what is variable elimination? It's an algorithm that uses dynamic programming to enumerate all configurations or assignments. Okay, and it works for both types of graphical models. So what do I mean? I put in the word dynamic programming. Okay, and I said dynamic programming is used to avoid enumerating all configurations or assignments. So what does it mean? All I mean is the following, right? If I have a graph with let's say I have a graph with 4 nodes, right? And I want to compute the probability of A, right? Then I need sum over B, C, and D of the joint probability. Right? Is that fine? I hope there should not be confusion here. What I'm saying is that when I do the summation, it's actually a short form. So if you really want to be, you need to write 3, right? So B in its set, let's say B is a binary random variable, 0 to 1, and D is in the set, 0 to 1, and maybe even C is in the set, 0 to 1, of that joint probability. So that's actually that summation. Now, one naive way is to actually enumerate all the configurations. So there are 3 random variables, they're taking 2 values each. So there are 8 configurations, right? 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, all that. So there are 8 such configurations. So you can, for each of those 8 configurations, you can find this number and then sum it. And then you'll get the probability of A for a given A. And you can do that for every value of A. Let's say there are 2 values, and that's how you can compute, let's say, the marginal. Now, the whole point of variable elimination is to do that in a slightly clever way, and you'll see that that clever way is quite straightforward, and it is as follows, which is don't sum all the configurations simultaneously. So don't do this sum where you take a b value, a d value, a c value, and then for every such configuration evaluate the number. Do it one variable at a time. That's the idea. So let's look at an example. Okay, so we'll use I think we've used lowercase before as well to reduce notation clutter, because these are essentially a conditional distribution or a marginal distribution is essentially a function, right? For every value of a, if a takes 10 values, then it's a probability of a, which is just a vector, right? We'll also use factor graphs now. So this factor graph has 4 variables and 4 factors, and this factor graph can be from a directed probabilistic graphical model or an undirected probabilistic graphical model, right? Because the number of factors is the same as the number of variables, it can be from either. But we are not concerned about that at this point. So we are only concerned about inference. So let's say we want to compute. We know that the functional form will be probability of a, b, c, d to be this, right? We can read that off from the graph, right? So f1 is attached to 2 random variables, so it's f1 of a, b. f2 is attached to 2 random variables, sorry, 2 variable nodes, so it's f2 of b, c, and f4 is just attached to 1 variable node, so it's f4 of d, right? So, and there's a normalization factor because I don't know whether it's from a directed probabilistic graphical model or an undirected one. If it is a directed one, I don't need this because this will actually capture conditional independences. This will actually capture the, they don't need normalization, sorry. So let's say our objective is to find probability of a and b. Yeah. Okay, so that's a marginal. Do you agree with that? Okay. So we'll take one variable at a time. So let's take variable d. Let's compute probability of a, b, c. Okay. So I just picked d arbitrarily because there are only 2 choices: either pick sum over d or sum over c. Ideally, I'm supposed to sum over both c and d, but let me pick d first. Okay. So I have this joint and I need to sum over d, and I can see that if I substitute my factorization, these 2 factors don't involve d, right? So I just push the summation over d inside. Okay, and only retain terms which involve d, right? And we're going to compute this for all realizations of c. So this summation, this internal summation, I'm gonna, for every fixed value of c, I'm gonna compute this. Okay, and I'm gonna represent this as nu of d to c of c. It's just additional notation, but all it's saying is I'm calling it a nu of c. Let's focus on c because this is actually a vector. For every value of c, there is a number here, right? If I do the summation,
we are summing it for d, right? So we could use all the values of d.
All the values of d are gone, so d is gone. Once I sum over d, it's gone. So the remaining part is what? C is it's a function of c, right? Is that clear? So in terms of notation, I could have just wrote this as some, f5 of c or something. All I'm saying is just now d is gone from my equation. I only have some new function which is just a function of c. Specifically, I'm just representing as nu of c, but I'm representing the subscript as d to c because we'll see that we'll relate it to the graph later on. That's why. Okay. So given that, let's take the next step. We only have one more variable to get rid of. So that variable is c. So we'll do a summation over c, and we can do that by pushing the sum by taking out the term which don't involve c. So among these 2, only f1 is independent of c, so it comes out of the summation, right? It's common, and the remaining terms are going to be f2 of b, c, and this function which is left, which is a new function, which is nu of c, right? And again, we need to eliminate C because we are summing over C. So now the remaining, this whole thing is just a function of just B, right? And I'm just retaining that C to B notation, but just think of it as a function of B. Okay. So this is it. This is the algorithm, and this is more efficient than a very naive summing over all configurations. Okay, this is very straightforward, but you can already see some efficiency gains. Okay, why is that? If you look at, so I don't want to exhaustively enumerate why there is an efficiency gain. In the sense, let's say if you have 100 random variables, okay, all are binary valued, and they're all in this factored form, okay. Then, if all of them are binary, then you have 2 to the power 100 configurations. You need to do that sum naively, right? That's the naive version, which you should definitely avoid. And this version is going to sum for every pair of random variables essentially. Okay, it's actually just a sum over the realizations of one random variable, so 2 numbers, right? In my example, and so you'll see that actually the number of computations needed here is actually linear in the number of random variables. So something like 200 computations, or 100. Since there are 100 random variables, maybe 200 computations. Okay. So instead of doing a sum over 2 to the power 100, I'm saying you can do a sum with roughly 2 times 100 numbers. In that, I mean, I chose an example which is very conducive to me. I just said it's a joint distribution which are the factors which are just which are only on exactly pairs of random variables, and that's why I said there's a massive reduction. You can think about it offline why this is the case. Okay. Is that completely, I mean, are you able to appreciate the difference between 2 to the power 100 and 200? Okay. Okay, so that's variable elimination. In a sense, it's just a clever way of doing summations so that you don't do exhaustively enumerate all the configurations and do the summation. Now, actually, if you formally look at it, it's actually a special or an example or an application of something called dynamic programming. How many of you have seen dynamic programming before? Okay. So it's just, yeah. We will not go into dynamic programming, but what I'm saying is there's a reduction in the number of computations. So let's go to belief propagation, which is a more interesting algorithm. So what is belief propagation? It generalizes the idea that we've seen in variable elimination, and it's also called the sum product algorithm. It will give exact answers on graphs which are actually just trees. So the example that we saw of the factor graph, it was just a chain, right? There was a factor and a node and a factor and a variable node and so on. But if you had in general a tree, a huge tree with factors and nodes, then belief propagation is going to give you an exact answer. It can also be used for general factor graphs, but will give you potentially wrong answers. So that's why we'll get to the third method, which is based on sampling. Okay. So belief propagation, I don't know how many of you have heard the word belief propagation or some product algorithm before. Okay. So it's actually very interesting because in early 90s, there were people in communications theory who were trying to come up with really efficient channel codes. Okay, what are channel codes? These are just, if you have a message, you have a string, right? Let's say hello is a string, and you want to transmit across channel, like the air, through your cell phone, and somebody receives it. You cannot just send a string because the channel or the air acts as a disturbance, and it may flip the bit representations of those characters, and then instead of hello you may get some other word, right, if you decode it. So instead of sending the plain text, you kind of encode it for the channel and then decode it at the receiver's end. Okay. so there is noise involved, and so therefore there are noise random variables involved because of the channel. And in 93, people discovered that you can actually use this algorithm, belief propagation, or a variant of it, to actually decode a very good channel coding scheme. So there was one way to encode these plain texts, okay, which are called turbo codes, or there are other codes are called low density parity check codes. So these are some very good channel codes, in the sense converting from plain text or whatever your message is to other strings which can be sent into the channel, and then on the decoding side you can use an algorithm like this to really decode your message and get the most likely string, right? So that would be the argmax of your marginal problem or something like that. Okay. So anyway, I mean, I don't know about 4G, but 2G and 3G technologies, the decoding part is actually backed by belief propagation. And also, if you have done inference using hidden Markov models, which were the predominant technology for example, speech recognition before, let's say, the deep learning era, you would have a belief propagation variant, which is, I guess, called the Viterbi algorithm, to decode the most likely sequence. So when I speak and it's transformed to a text, there is a decoding process, and so there's a HMM involved there, and there is inference involved, and you will use some algorithm like this. Okay. Anyway, so coming back to belief propagation, we're gonna first go through an example and then look at the actual algorithm. So variable elaboration was quite simple, so I didn't spend too much time on it. So let's consider a graph which looks like this. Okay, so it has 5 factors and 5 random variables. Okay, and you can see that some factors are attached to just one variable node, and some factors have 3 variable nodes attached to it. Okay, so it's not just simple chain. That's what I'm saying. And now in this graph, or the joint distribution corresponding to this graph, I now want to compute the marginal p of a comma b. So it's very similar to what I was doing before. Okay. So to do so, the graphical aspect of this joint distribution will become very important, and we'll introduce this notion of messages and message passing. Okay, it's a very interesting jargon that these guys use. So beliefs are just are things which are related to probability. So probability is local to the nodes, and the messages are going to be information you pass across nodes to figure out, for example, in this case, the joint probability, and in this case, the marginal, and so on. So we'll see what the messages are. The messages are actually just functions of random variables. So as in what you've already seen before. So nu of c is a message actually. So I'm just adding some annotation here, and we're going to pass through that annotation in the next couple of slides. So we'll have this notion of messages, and messages are just functions that are passed from one node to the other. Okay. So if you ignore the red part, this is the original graph, factor graph. Okay. It has the squares, square nodes, which are the factors, and circular nodes, which are the variables. Okay. But they are still nodes of this graph, and each node or all these nodes are going to pass messages, okay, to their neighbors, such that we'll accomplish our original task, which is to estimate, or not estimate, to actually compute probability of a comma b, okay, the marginal distribution. So how will we do that? Again, we'll start from what we already know. In the sense, from this graph, we can read off precisely what that factorization was, right? Which we wrote in the last slide. So let's slowly start constructing messages. So we want p of a comma b, okay, and to get p of a comma b, I just need to sum over all the irrelevant variables, which is c, d, and e, right? The only 3 other variables which are irrelevant. I need to do the summation, and I'm going to call this whole term nu of b, okay, and I'm going to use couple of things. So I'm going to subscript it with notation f2 and b, It will become clear later on, but for now I'm just saying this is a function, okay? Function of whatever is not summed over. So you can see that there's B, C, D here, C, D, and D and E here. I'm summing over three of those arguments, so the remaining argument is just B, right? Just B. So I just rewrote the new function nu of f2 to b of b. I just rewrote this here, but what I did is I sent the summation over e because the first three terms don't involve e. I sent e all the way to the last term, right? Very reminiscent of variable elimination. Very straightforward. Now I'm going to call this function nu of c to f2 of c. Okay. So basically this is a function of c. So just think of it as another function of c. I'm just renaming that function to nu of c to f2. Okay. We'll discuss the subscript notation in the next slide, but I'm just saying that this is a function of c, and we're going to call the remaining part. Once I do the summation over e, this is going to be a function of d, and this is a function of d. So I'm just going to call this a nu of d. Okay. And again, I'm introducing some subscript. So in fact, if you notice, a subscript is basically either one of the arguments. Sorry, on either side could be one of the arguments. So for example, here the subscript is just b because the argument is b. Here on the left side the subscript is d because the argument is d. But we'll get to how the subscripts are represented later. The reason why we are introducing this is to automate it into a computational algorithm, right? So we'll get to that. So what I'm saying is, I had this original joint distribution. I sent the irrelevant variable summation to, I just called it a new function name. And that new function, again, I recursively kind of sent, for example, e inside, the summation over e inside, and called and defined new additional two other new function names. So total 3 functions have defined here, right? I just repeat that on this slide. So nu of f2 to b is the same thing that we saw in the previous slide. That we saw here, this and this. And the why I've chosen this notation for this factor, sorry, this term, and this notation for this term is because if I write it in those terms, there's a pattern which is coming here, which is there's an f2 which was there, which was not, f2 which was there before. There was f3 which was also there before, but I've represented it as a nu of f2 with f2 on the right hand side in the subscript. And for this term, I've again written this as a nu of d to f2, where f2 is again on the right hand side. Okay, I've just replaced the functions with new definitions, right? But I wanted to highlight now the indices of these functions, or whatever subscripts of these functions. So let's focus on f2, okay? And I'm again repeating the same thing here. So let's focus on f2, okay? So what exactly am I doing here? In the graph, nu of f2 to b is over here. Can you see the notation? You can. Okay. So nu of f2 is here, right? F2 is this square node here. Okay. So I'm going to call this as a message, and this message is composed as follows. This message is summing over all the irrelevant variables which are related to this factor, which are related to this node. So irrelevant variables here are basically the other variable nodes other than b, right? I want to pass a message to b, but I'm also connected to two other variable nodes c and d. So let me sum over c and d. Since I'm a factor node, I will have a factor associated with me. So that's the factor f2 of bcd. And I'm going to multiply that factor with two messages which are from the c variable node and the d variable node. So that's nu of c to f2 and nu of d to f2. Okay. In a sense, the computation that's happening here in terms of me trying to send a message to b is based on the factor that I already know and two messages that I've received. from all the other variable nodes other than the factor that I want to send a message to, right? Or if you want to write it more generally, it's basically a summation over all variables that this factor is involved with, except for the variable that I want to send a message to, right? I'm sending a message to B, so I want to sum over everybody else related to my factor. So if I want to send a message to B, it's a sum over C and D. And a product of all the neighbors of the factor except B, of the messages that are received from those neighbors, right? So who are the neighbors of the factor F2? B, C, and D. But I'm sending the message to B, so I will not consider that. And I'll take a product of all the messages that I've received from the other variable nodes. Okay. So for example, this product is essentially these two terms, right? C and D sent me some messages. We are going in a recursive way. C and D sent me some messages, so that's this product. And I have one factor here, so that is just represented as phi of f, and script or mathcal f is just all the variables that the factor is defined over. And I'm going to sum over all the variables except the guy I'm sending the message to. Okay, that's the general form. Is that clear? Confusing? Okay. Because we're going to recurse one level now. So we focused on this factor, F2, and this was the expression, and we said this is the general form of that expression. And now we're going to focus on how did we get this. So this is a message from a factor to a variable. Given this general form, I can create messages from factors to variables. For example, from this factor to this variable. For example, from this factor to this variable, this factor to this variable, this factor to this variable, for example, or any other, like this factor to this variable. I can do once I've written this general form, I can send messages from factors to variables. That's what I want to get across from this slide. And now let's focus on the messages which are from variable to factors, right? So in the previous slide, I sent a message from variable C to factor F2, a variable D to factor F2. So now we're going to focus on how did those messages get generated. Okay. Ultimately, they'll get generated all the way to the end. We'll see what the initial conditions are, but where do these messages get generated? So let's focus on the message being sent from variable D to node F2. Okay. So this function or this message was, if you look at the previous two slides, this was just f phi of D times the sum over E of f4 of D comma E. That's how I defined this message. Okay. Now I'm going to now call this f phi of D a new variable, new message name. I'm going to call it a message. Okay. And I'm going to call it f phi to D of new of D. And this, when I sum over E, the remaining, this is just going to be a function of D. I'm going to call it mu of f4 to D. Okay. Which means that my message from variable D to factor F2, from D to F2, is going to be a product of a message from a factor f phi to D and a factor from f4 to D. Okay. Just repeating the same thing. This was the special case for the variable D, which was sending message to some other factor, in this case factor 2. And if you actually just think of it, it's these two are just coming out as products. So I'm going to do a product over all the neighbors of the variable node except the factor that I want to send the message to, of the messages that I've received from these from other factors. So every variable node is connected to some factors, right? Maybe one factor, maybe more than one factor. I want to send a message to one factor, so I'll pick that factor and keep the other factors on the side. And whatever messages these other factors send me, I'm just going to compute a product and send it to this one factor. Okay. That's the computation of all the messages. So if I could compute this in the special case this, okay, and that feeds in over here, and I could compute this. Then I can compute this, and then I can go back and sorry, one more slide. I can go back and compute P of A comma B. In the sense, if you see, P of A comma B is just a product of F1 times a message that was received from F2 to B, and the message from F2 to B, we know what it was. It was a composition of the current factor times some other messages that F2 received, and we know what messages get sent from sorry, that was general form. What messages get sent from variables to F2, right? So this completely describes what messages are sent forth to compute P of A comma B. Do you agree or not? Any questions in terms of conceptual understanding of what is this message and what's happening in this computation? Okay, let's see. So I computed P of A comma B. Now let's say I want to extend more. I want to compute just P of A. Okay. Then P of A is going to be equal to the message that F1 sends to A. So F1 is over here. So P of A is going to be, I'm just defining this. So, but P of A, we remember, is just the sum, was P of A comma B was just this term on the inside, right? If you remember. If I sum over B, then I'm going to get P of A, right? I'm going to just call this nu of F1 to A, and I'm just writing that over there. That's all. That's by just definition. So if you think of this, then all I'm trying to compute is a message from a factor to a variable node, and that form we've already seen. A message from a factor to a variable node. No, P of A is this, and we're calling this nu of F1 to A. What I'm saying is this factor. So we care about so nu of B to F1. Okay. B to F1 is the message that was passed from the variable node B to F1 that existed from before, right? That was the original definition. Since B was only connected to two factors, B received one message, which was F2 to B, right? I'm just gonna pass that message forward to F1. Okay. So nu of F2 to B is just passed to the F1 factor node. So nu of B to F1 is the same as nu of F2 to B. Okay. So what I'm saying is, if we had P of A comma B, which was just a product of two terms, which was the node, which was the factor at the node, which was the product of F1 of A comma B, and a message that we received from the rest of the graph, which was the message from B to, which was the message from F2 to B, right? Which was this. Okay, yeah, that's a message from F2 to B. I just replaced that with a message from B to F1 over there. So let's look at the general algorithm, the generalization, and then we'll come back to this example to kind of reinforce how belief propagation works. So we described the concept of messages via an example, which was we wanted to compute probability of A comma B or probability of A, which was the last part. We'll summarize the algorithm in general. So how is the algorithm actually working? I just defined messages, and I said for a given graph, I just showed you I can just redefine the function computations as messages, and I'm done. Which was just, you can think of it as just a fancy way to re-express variable elimination, but there is a difference. So let's look at the general form. So we'll start from somewhere. Okay. So these messages have to start from somewhere, right? They can't be like, for example, what is the message being received by this last guy? Maybe there's a message being received from D. but what is the message being sent from, let's say, this node, this factor node to D, right? F5 to D. It's not clear. So that's what we're going to capture in the initialization. What is the message being sent from, let's say, this node to that factor node? We'll get to that. So that's the initialization, and then we'll kind of write the variable to factor messages and factor to variable messages. So with the whole point being, we want to do efficient inference just as before. So what is initialization? So initialization is as follows. So messages from leaf node factors, okay, nodes at the extreme end which are only connected to let's say one other node, right? For example, if it's a square, if it's a factor node, it's connected to a variable node. Okay. Then the message from this factor node to the variable will just be the factor itself, okay, the term itself. You remember that if this was the notation in the graph, then this factor has only one argument. So there is an f of that variable, right? That term there. So that itself is going to be just a message that will be passed from that factor to the node. And if you want to pass messages from leaf node which are variables, okay, then the message is just going to be initialized to 1, which is the message from a variable to, if it's only connected to one factor, then the message from x to f for all values of x will be equal to 1. Okay, that's the initialization. And the variable to factor messages that we've already seen is as follows. So here is the variable, it needs to pass a message. Okay, let's focus on, so this variable is connected to 4 factors, but for the time being I only care about sending a message to one of these factors, let's say. Okay, I mean ultimately I may be interested in sending messages to all the factors, but let's say I'm interested in sending the message to a factor f. Okay, how am I going to compute the message? This variable is going to just product the sum of all the messages that it receives. Okay, it could receive a message from this guy as well, right, due to symmetry, but to generate a message from this variable node to this factor node, I'm just going to take a product of all the messages from all the other factor nodes that I am connected to. That's all. So that's the notation here. Neighbors of the variable except the factor node that I want to send the message to. I'm just going to product the factors. Okay, and these factors have to be functions of the same thing. Okay, that's why I can product them element wise. Okay, otherwise it becomes fuzzy, right? So is this clear how a variable to a factor message is generated? And the next component is going to be a message from a factor to a variable, right? So let's say a factor is connected to 4 variables in this case, okay, and I need to send a message to one of the variables. Let's say x is one of the variables. I may be interested in sending messages to all of them, and in fact I will be, but let's focus on one case. Let's say I want to send a message from this factor f to one node x. Then the way I'm going to compute is, first I'm going to get my factor term, which is phi of f, which is a function of many different potential variables, right? There could be many arguments of this factor. For example, so I'll have a factor here, so which is phi of f. I will get messages from the other variable nodes we saw in the previous slide. I'm just going to take a product of them, excluding the potential message that I could have gotten from x itself, right, because of symmetry. So I'm only going to take a product of all the neighbors of my factor except the node that I want to send a message to. I'm going to multiply these two, okay, and I'm going to sum over all the irrelevant variables, in the sense all the variables which are not the same as the variable node I'm sending a message to, okay, and that's it. That's my message from a factor to a variable. So those are the 3 key blocks. Initialize. If I don't have a if I have just connection to one factor or a one variable, then how do I start getting sending a message? And at any other part of the graph, I'll always have a factor connected to potentially two variables, or every variable node connected to at least two factors, then I'm just saying how I can get a message from one side and send a message to the other side. Okay, and I can do this symmetrically. I can now change x to y3 and do the same computation. Again, change flip y2 on this side and x on that side, do the same computation, and so on. So there are a lot of computations happening, but for a snapshot, I'm just showing you how to generate a message, right? So those are messages. I can compute them for all my nodes, factor nodes or variable nodes. There's this notion of ordering of messages, right? I said I can compute these messages. I told you how to initialize, but I didn't tell you how these messages are multiplied, right? Because for a node, I may need messages from, let's say in this previous example, not example, but in the previous general formula, I will need messages from these three guys. So I'll have to wait till I get the messages from everybody else in my neighborhood except to the guy I'm sending a message to actually send a message, right? So how do you do that? At least for trees, it's kind of not actually complicated. For trees, there is nothing special that you need to do. You just need to follow this procedure, which is just go from leaves to a designated root. You just designate one of your nodes to be a root. Okay. So let's say x3 is a root here. Just go from all the leaves. Since it's a tree, there will be leaves, right? So you just pass messages from leaves to the root, and then you again pass messages from root to the leaves. Okay. You can see that if you do this, there is no issue of not having a message to compute to forward pass a message. In the sense, this guy, this variable will get messages from these two factors while sending a message to the next factor. Okay. So there is no issue of not having messages from which to compute a message to forward to the next person, right? Now, how do you get the marginal, right? We kind of sidetracked a bit because in the example I said we are computing probability of a comma b, and I specifically designated some functions to be messages, and I said okay, we get a comma b, or even probability of a. And then I went to the general algorithm where I said we'll initialize, we'll see the messages from variables to factors, we'll see the messages from factors to variables. We saw that, but then since the messages from factors to variables or the variables to factors involved everybody in the neighborhood of those nodes except for the guy you're sending the message to in both versions, we had this issue of how do you order messages. But as I said, for trees, you just start from leaves, go to some designated node and root node, and then from that root node you backward pass the messages. For example, you can also take x2 to be the designated root node. You send messages this way once, and then you send back the messages from x2, right? But how do you compute the marginal? Okay. So marginals are actually, and that's what we saw in the example. We were computing probability of a, right, or probability of a comma b. So the marginal is actually the same as what we saw before. The marginal is actually equal to. So marginals are always going to be functions of a variable, right? So the marginal, which is p of x, is just going to be the product of all the messages it receives. All the messages, no exclusion of factors anymore. Okay. So if you remember messages, yeah.
In the previous example, if you wanted to calculate marginal of A and E.
Marginal of A and E. Okay.
So how would you do this? Because in that A and B, you consider A and B, they were adjacent to each other. So all the messages were directed towards.
So actually, this example is just for a marginal for a single random variable. What I'm showing here. We'll get to marginal of A and E. So A and E is also will not. Okay, let's look at. So here, right? You're asking, you want to find probability of A comma E. You can go through the same thing. I mean, you'll pass the same messages, but you have to stop where. Yeah, you'll have factors. Finally, you'll have a compounded term which will have like some other f of a comma e remaining. So it's the same thing as before. So you pass these same messages as before, okay? But you will not sum over e. That's the only thing left.
There can be two iterations, one on coming to A and
Yes. Yeah, you will have those iterations. No, it's the same iterations as before. So this is the same as for computing any marginal. It's the same thing. Okay. It's just that these messages are fixed, right? They are not dependent on which marginal you're computing. When I showed you, this has nothing to do with whether I'm computing marginal of x1 or x2 or a margin of x1, x4 or anything like that. I'm just saying if you have a tree, which is this factor graph, I can just compute these messages in one direction up to a root, designate a root, go up to root, and then come back, right? With these messages, I can compute now marginals. And I was just showing you one of the marginals here because it has a nice form. But if you want to get marginals with nodes which are far away, it's again going to be product of these messages, but in a slightly different way. So
summations will be based on the nodes.
We are not doing that, right? We are ignoring what the marginal question was and doing this, right? Generating the messages. We were doing the summation carefully in the example, right? But here we are not, right? I said in this template we initialize, start from the leaf variables, pass messages. If it's a variable to a factor, do it one way. If it's a factor to a variable, do it the other way, right? So this has nothing to do with which marginal question you're asking. And this template is useful for computing marginals of just single random variables. Okay. Now your question was A and E. A and E, one way to do it is to actually just think of these two as one node, one super node. Okay. And then you'll have a graph. In this case, you'll have a graph with remaining parts outside the outside that super node, right? And you just pass messages the same way. You just club A and E together to call it a super node. So when you put A and E together, you will have this factor, can't read it, which is F4 and F1. Okay, those are the only links going into the rest of the graph, right? So you can just club them together because those will include A and E, right? Do you understand what I'm saying? But what happens is if you club A and E together, at least in this example, it's not going to be a tree anymore, and so you can apply belief propagation, but it's not guaranteed to give you the right marginal. So that's why focusing on trees. On trees, you can say, for example, I can compute A comma B. I can compute, let's say, anything on which has a single path. But if once I club A and E, I'll get to. You can see that, right? If I put A and E together, I'll have a path over here, and I'll have also a path through D. So two paths are going to be there. Anyway, that's for that clarity. Any other question? Yeah.
So here, if we assume A to E are random variables, binary random variables, right?
Yeah. These can be anything. Doesn't have to be.
Assume they're binary random
Okay.
variables.
Yeah.
I'm computing the marginals for all variables A through E.
This procedure that I showed you, where, like, let's say for this graph, it's the same for the other graph. Pick some, okay, in the other graph, let's actually focus on the other graph. There's a big picture here, right? Yeah. Pick any node, send all the messages to that node first. Let's say in this case, we pick node A, send all the messages to A, and then send all the messages back. Okay. Once you do that, you can compute the margin over A as just a product of all the incoming messages. In this case, there's only one incoming message from F1, so that itself is the marginal.
Okay, so when I'm going to compute the marginal of A,
Yeah.
then after I receive all messages to A and send all messages back, the system should be in a steady state, right?
It is, right? Because there is no issue with when I send it in one direction, there is no issue of lag, right? So when I'm sending in one direction, this guy will get a message from all its descendants. So there is no issue of not having messages.
Okay. So no, my question was, so if I have to compute the margin of another variable, then I should recompute all the messages.
No, that's the niceness of this belief propagation algorithm. In the sense, if you do this, pick some node as root, let's say A, you pass all these messages to one direction, and then you pass the messages back, right, to the leaf nodes. Then, you'll have messages like for this guy, it will have 2 input messages at the end of the day. This guy will have 3 input messages, right? you can just use those messages to compute marginals for all A, B, C, D, E at the same time.
So all it needs is one full propagation, either
One pass, two passes. Yeah, 2 passes is enough to compute marginals for all the random variables. Okay, which was not the case for variable elimination anyway. But variable elimination is essentially a special case of this, because all we are doing is pass sums and judiciously choose where the sums are happening. Okay. If you see, the sums are actually happening in the passing of message from factor to a variable. Yeah, this is the summation that's happening, right? So that's why it's actually called a sum product algorithm, because there's a sum over here and a product over here. But yeah. So let's look at one more quick example. Let's say we want to compute. Okay, actually, let's take a break. We'll get to this in 2 minutes.
Paper are you referencing
Paper.
or you say that the Andres and Shio?
Oh, it's a computer vision course. I have put a link somewhere, but I'm not expanding the link here.
I see. Okay. Thank you.
These are just graphical model courses specialized for, like these guys are specialized for vision,
I see.
which is for image processing. So the same thing that you're doing, you can do. We saw classification in the class, but there are many other vision problems, right? Image segmentation, where you segment parts of the image as being sky, ground, an object, and so on. You can use these methods. We are not going into the details here.
Right.
thank you.
Compute the complexity of this advanced tic-tac-toe, like how many moves are possible. So, according to my estimates, it's coming to some 10 power 50 or something.
50. Okay, not bad.
Is it doable with this? I mean, I might probably not be able to go to that side. I'll have to probably do
You
something.
can always restrict moves, right? I mean, let's see.
First of all, can you check whether if it's correct or not?
The combination of the
I'll tell you how I did it. It's like I did it as simply 9 factorial or 9. Because for every tic-tac-toe it will be 9 factorial. And once you start, essentially you are fixing it. There are some cases where it will extend, because suppose if you go to a case where that is solved, then you have the rest of the squares. But I'm telling, like a lower bound will be that much.
Okay. So 9 factorial is, or 9 is 10 to the power 50? Okay.
Because 9 factorial is itself 360.
Yeah.
So that power is coming to roughly that much.
Could be. Let's discuss today. Yeah.
So for this one, this slide,
Its slide is 69. Okay. 71, 69. Yeah, 69.
this one, why is it, I don't understand this one. What does that mean?
So we just showed a factor which is connected to 4 variables, but whatever will be the number of variables, it can be 2 variables. A factor is always connected to variables, right?
Yeah.
First thing. In this case, it's connected to, let's say, 4 variables, or not in the general formula in this case, let's say. Now, if it wants to pass a message to any node, let's pick one of the variables to be where I want to pass the message to. You have to actually originally pass message to this guy as well, but let's focus on passing a message from this to this.
Okay.
Now, to pass a message, to construct a message and pass it to that node, all I need to do is take the messages from other variable nodes,
Yes.
not this guy. So that is this product. Okay. All the messages coming in from the other variable nodes is always going to be new of those y's. Okay. This part is clear. These 3 messages
sum
are this
of
product. Yeah. There is no sum happening. This is just a product. There are 3 messages, so 3 product terms here.
Okay.
Now what is this? This is just a factor associated with the factor node itself. Like if you remember the factor, okay, this is 69, right?
It's like yeah.
If you go, yeah, let's pick this example. Let's say this. Let's say this is a factor. Oh
Yeah.
shit! If this is a factor, then
The functions will be this, right?
yeah, this f2 is the factor related to that f2 and f2. This f2 is the same. Okay, that is that phi. Okay, this sorry, where is
So this entire part is
no,
the phi.
this f2 is a phi, and the remaining part is going to be the product term. So that's what we see here, right? This f2 is at phi, and these two are the two messages that it received from the variables. So these are the messages from the variables, these two, and this is the factor local to that node itself. And so this summation is over everything else. So if I'm going to pass a message to B, then I should sum over everything else other than B. So that's what's happening. So in fact, the same thing is rewritten here. So this term, this equation here, is written here, and if you map it to the general form, this f2 is the same as phi of f of script f. Script f minus x is the same as c comma d, because it's bcd, and bcd minus b is going to be just cd, because you're sending a message to b.
Yeah, I'm saying
So b is x, right? I want to sum over everything except x. So I want to sum over everything except b. So since there are bcd, I want to sum over everything which is just cd. So this phi f is the same as f2, and these two terms are the product, two messages that I got from other variable nodes, other than the one I'm sending a message to. Like this guy wants to send a message to B, then I need to get messages from C and D, which are these two.
so. These is the message, some of the message. But
Product
this,
of the messages.
Yeah, and then this one.
This is a summation of local variables which are not. If I'm sending a message to B, then I should remove all the variables which are not B.
Yes.
So that is that sum. It's like marginalization. Because it's a function of C, B, C, and D, you have to get rid of C and D. So, for example, this is going to be a function of C, this is going to be a function of D, but you only want a function of D to be sent forward to, let's say, this guy, this guy. So, you have to sum over everything else, which in this case is CD. Basically, sum over all variables which are not relevant to the guy who you are sending a message to.
My confusions is between
The general formula is this.
the message come from here.
Yeah.
These two things is the same thing, right? They transmit message. So I want
every node sends a message. The square node also sends a message to a variable, because square node can only send messages to variables.
Yes.
So this is how it would send a message. Now circular nodes can also send messages, but they're only connected to squares, so they can send a message this way, which is just the product. So there are two types of messages. Messages from variables to products is just a product of incoming variables.
Yeah.
And from factor to variables is a product times the local factor that it has, and you sum over all variables which are not relevant to the guy you are passing the message to forward. Right? X is the guy you want to send a message to. You want to sum over all other variables that are related to this factor, which in this case is y1, y2, and y3. So this is sum over y1, y2, y3.
From these variables.
Yeah, you sum over y1, y2, y3 of the factor involving y1, y2, y3, x times all the messages you got from y1 times message you got from y2 times message you got from y3. Yeah.
Okay. Thank you.
Okay.
Professor,
Yeah.
I need. Can you give any access for GPU? Because for running, we are doing the state farm thing, driver detection.
Okay. Send me an email. We'll talk about this. Send me an email.
Because it's taking around 20 hours to just run the pre-trained data.
Okay. Okay.
And if we made any modification, then it will again take whole 24, 25 hours. Minimum.
Send me an email. I'll see what.
One more thing. Global marker graph you showed like this rectangle. It's square, and this node is not connected to that fourth node. Starting.
Yeah.
Global, in this.
Which node?
In this, one is not connected with 4. Then how you are saying that one is independent of?
No, given 4.
Okay. You said only in the previous slide. You said
Given something, two parts are disconnected.
Okay.
So you can visually see, right? If I get rid of 4, these have no way to. There is no path from any of these variables to any of those variables. So these two are conditionally independent.
So it should not be like that. One should be at least connected with 4 or something
No,
like
no.
that. No.
No,
So
it's
the
nothing
whole
to do
set
with
will be
condition on
disconnected.
4. Yeah, 2 separated
Okay.
sets are. It's basically like cutting a graph into 3 parts. You take off the graph. If you take off one part, if two parts are like completely disjointed, then they are conditionally independent. That's all.
Thank you.
Okay. So we're going to resume. So let's look at the last part of inference. So we have seen variable elimination, which was nice for simple graphs, but you had to actually figure out how to eliminate variables, right? I didn't tell you how to eliminate variables in the variable elimination algorithm, and there are 2 plus signs, but ignore them. So in variable elimination, you really had to figure out which variables to eliminate in which order. So the order in which you chose the variables kind of determines how much time you will take to actually find the marginal or the conditional distribution or things like that. Okay. In the belief propagation, at least if it's a tree graph, you know how to process messages, and so there is no ordering issue, right? You start from leaves, get to some designated root node, and then go back to the leaves, right? So that was just for computing marginals. There is actually another variant of this belief propagation algorithm called the max product algorithm. Okay. So in this case, what we want to find is an answer to this question. So we want to find an answer to this question, which is find that configuration which maximizes my, for example, which maximizes the probability number that is assigned to that configuration. Okay, because I assign a number for all configurations in my configurations or realizations of my set of random variables, right? So I want to find that configuration which is the highest value. Now you can always look up for each configuration what the number is and figure out which one is the maximum by kind of a lookup operation, but that's very, very inefficient, right? So again, we can modify the sum product algorithm or the belief propagation algorithm that we saw before to achieve this, to figure out what is the maximum. Okay. It again has 3 ingredients: initialization, variable to factor messages, and factor to variable messages. In fact, these messages are the same as before, except for one set of messages. So initialization is the same. Okay. If you're starting from a factor or if you're starting from a node, this is the same as before. Variable to factor messages that we saw was accumulate all the messages that I got from other factors, product them, multiply them, and just send it to the next to the factor of interest. Right. That was the variable to factor message. So it was just a product. Right. There was no operation going on. The interesting part is the factor to variable message, which had a summation, right? Which had a summation over the local variables, which are unrelated to the message that you're sending to the target node. Okay, so let's look at max product algorithm. So the factor to variable message it has one change from before, which is going to be you will get messages from other factors just as before. So other variables just as before. So these variables sent you, let's say in this case there were 3 other variables, so these sent you 3 messages. You take the product of those 3. You have a local factor phi f of script f that you can multiply with them first, and then you're going to take a maximum over all variables, not except the target variable to whom you are trying to send a message, and you're going to just send only that as the message to the target. Okay. So before I was doing a sum over all variables, which was not the target variable. Now I'm going to take a maximum over all variables in which are present except the target variable, and send that will still be a function of the target variable, because for every target variable there will be a max, right? So it will still be a function of the target variable. I can send it forward to the variable of interest x. Okay. So that's the only change. Instead of a summation, I changed to a max. When I do this max, I can also remember which variables achieved that max, because I didn't tell you how to compute this max. It could be even exhaustively. I need to compute that max. So when I do that max operation over this whole term, I'll have some configuration of some. Let's say in this case, in this example, it's going to be some y1 star, some y2 star, some y3 star, which achieved the maximum for each x. So I'm going to remember them. Okay, that's all. So if I remember them, I can backtrack and figure out the maximum configuration. Okay. So two key things. One was that we just changed the summation to maximum, and the second thing is trying to remember what, if I did a max operation, I want to remember not just the function, the message that I'm going to send forward, but also the realizations which achieved that maximum. That's all. And again, the maximum computation is the same. I mean, this is in fact is the same as before. So for example, for a single node marginal, we already saw that we just had to multiply all the messages that we got from all the factors. We already saw this. So the maximum of that would be just a single node maximum. So that's nothing different from what we saw before. But if you want to get the maximum over a configuration, let's say a comma b or a comma b comma c or something, then you'll have to remember what was the max that happened before. Okay. Any questions for belief propagation? Okay. So belief propagation is an exact algorithm for tree structured factor graphs. Now we'll stop with the notion of factor graphs. We'll kind of forget we have graphs and try to figure out how to do inference, because even if I have a joint distribution, even if I did not have a factor graph representation or even a directed or undirected graph representation, as long as I know that it is as long as I have some handle over this joint representation, it could be joint distribution. For example, it could be, as I said in the previous parts, we saw that we had the handle on that joint distribution as a product of bunch of terms. Right? In the directed case, we had a product of a bunch of conditional distributions. In the undirected case, it's a product of bunch of potentials. But we had a handle on the representation, right? For the third set of techniques, we will not really need the notion of a factor graph. That's all. So that means this is actually a very general technique, and so some of you may have already seen these techniques from before. So we'll as we go through, we'll see that. So BP and variable elimination work on tree structured factor graphs, and we'll now look at approximate methods, in particular numerical sampling methods, to perform approximate inference. Okay, and so the first notion is, okay, let's get to Markov chain later. Let's focus on what are Monte Carlo methods, right? What is Monte Carlo? What is a Monte Carlo method? It's very straightforward as well. Let's say we want to, so in the previous cases we were looking at computing marginals and let's say even conditional distributions we haven't looked at, but they are very similar to computing marginals, because the conditional distribution is just like if you have a conditional distribution of A given B, then it's just the product of A comma B, it's a ratio of something like this, right? So that's why we focus on marginals, because conditionals are further functions of marginals. Now, let's say you want to compute the expectation. Okay, so expectation by definition is this, or if it's a discrete random variable, then it's that. Okay, Monte Carlo methods are this idea where you draw independent samples, L independent samples from your distribution of interest, so from P, and then just replace the integral or the finite sum, integral or the sum with the summation over the finite set of samples. So we have an f hat, which is going to be an estimate of this expectation, which is just going to be 1 by L times the sum over all f evaluated at these L independent samples. Okay. So as long as x is actually drawn from P, you can actually show that expectation of f hat is the same as expectation of f, which means that this estimator is unbiased, but the core point is Monte Carlo methods are just methods where you approximate integrals or summations or even these functions with functions of samples, finite number of samples. Okay, that's straightforward, and you might have seen this before. How many of you have already seen Monte Carlo methods? Okay, so that's Monte Carlo methods for you. We're going to now look at a couple of general techniques. One is rejection sampling and one is importance sampling, which are what I would call rejection sampling is a Monte Carlo method, and importance sampling is also, I guess, an extension to the vanilla Monte Carlo procedure that we saw in the last slide. And then we'll get to better sampling methods which involve Markov chains, and predominantly we'll look at Gibbs sampling and Metropolis Hastings sampling. Okay, so at least this example should motivate how we can get to estimations of maybe not marginals and conditional distributions, but at least functions of distributions, right? If I wanted to compute function of any distribution, let's say expectation is a function of a distribution, then I can do it by getting samples, and that's why we are focusing on sampling, and that's why all these are sampling methods. Okay, so what is rejection sampling? So rejection sampling is a very straightforward idea as well. So here, what do you do? So let's say the red curve is a one-dimensional distribution that we care about. Okay, we care about computing, let's say, some function of that distribution. Let's say the expectation, as we saw in the previous slide. How are we going to do it? We're going to come up with another distribution, which is going to be this Q. Okay, Q is a distribution, one-dimensional distribution as well. We're going to scale it by a factor k, such that that one-dimensional distribution is always greater than p of x for all values of x. Okay, or in this case z for all values of z. Okay, it doesn't matter. But what I'm saying is you come up with a blue curve which is going to be greater than the red curve. Okay, so you find the q of z. Now this is going to be hopefully this is going to be easy to sample. For example, you can see that this looks like a Gaussian, right? So whereas this is maybe hard to encode. Then you draw a sample from that distribution, okay, q of z, and then you look at the value of k times q of z. Okay, it's going to be a number between 0 to k, because q of z is a value which is between 0 to 1. It's a probability density function, right? So we're going to draw a uniform sample, uniform random variable, draw a realization of that between 0 to k times q of z naught. Okay, so we drew z naught from a proposal distribution. We use that to represent the interval, like one end of the interval. From that we draw a uniform random variable. Okay, and check whether the uniform random variable is greater than p of z naught. Okay, so given z naught, we can compute k of q naught and a p tilde of z naught, right? So those two are just functions of z naught. And I'm just checking whether this random variable is exceeding p of z naught or not. I'm using p tilde because sometimes you may not even evaluate p of z. You may only get, for example, in the undirected graphical models, you may not know the normalization constant. So in this case, it will be scaled up, right? So if u is greater than p of z naught, you reject the sample, and if u is smaller than p of z naught, then you accept the sample. Okay, so that's it. So basically, from this blue curve, draw some z naught, so that z naught is here. Then from this vertical line here, this interval, draw a u naught in this case, and see where the u naught falls, whether it's below the red intersection point or above the red intersection point. If it's above, you reject. If it's below, you accept. Okay, and we can look at the acceptance probability here. So if z is drawn from q, it's going to be since I'm checking the random variable whether it's greater than q of z or not. The probability of acceptance is actually p of z divided by k of qz divided by k times qz. Okay, that's because in this diagram, as you can see, this is a probability. This is the region where I'll accept among the whole interval. So the probability of me accepting is this divided by the whole interval, right? That's what that is. So you can actually probability of acceptance is wherever z falls. So that's why I'm integrating over all z. Wherever z falls, the probability of acceptance given z. So that's just going to be 1 by k. Okay. So I'm going to accept more samples if k is going to be close to 1. Okay. So why we are computing probability of acceptance and we are seeing that it's an inverse related to k is because in high dimensions it's you're going to reject a lot of samples. That's the intuition, because if my probability of acceptance for one dimensional sampling is 1 by k and k is a value greater than 1, so you can imagine in multiple dimensions it's going to be 1 by k to the power d, and that's going to some number, small number to the power, let's say 100, is going to send the acceptance to 0 almost. Okay, I mean, in fact, I have a slide here. So let's say p of x is Gaussian with some covariance, and q of x is also Gaussian with some covariance. So in fact, p of x need not be Gaussian. That's the whole point, right? If you don't know how to sample from p, that's when you do rejection sampling. But let's say p of x is Gaussian for a theoretical argument. Let's say also that the variance of q of x, that distribution, is greater than the variance of p, because it has to be on top of q, right? In d dimensions, you will see that k is actually equal to sigma q divided by sigma p to the power d. Okay, which is a value which increases very sharply with d, right? In the sense 1 by k decreases very sharply with d. So k is like 20,000 for d is 1,000, and then you can see the probability of acceptance is almost 0. So if you try to sample this way, then you'll not get actually any samples. You'll get 1 out of 20,000 samples. Okay, you sample 20,000 times from your distribution from which you can actually sample, which is a Gaussian, but you'll only get one sample which is actually a sample with which you can actually compute the Monte Carlo average, let's say, for the expectation. Okay. So that's rejection sampling. Any questions? So it's straightforward, but if you've not seen it, then you should check offline. Okay. The second Monte Carlo method is what is called importance sampling. So importance sampling is just a small trick that you play with the original Monte Carlo averaging that you were doing. So what was the original Monte Carlo averaging? If our objective was this expectation, then we would sample L points and do a summation of 1 by L is missing, so 1 by L times f of L. 1 by L is missing because there's a p of ZL there. So if the original objective was to compute an expectation with respect to a distribution, we can sample L points from the distribution and take an average, right? Is this formula clear? It's the same as the previous Monte Carlo averaging formula, except there's no 1 by L because I'm explicitly taking the probability of Z of that sample point if I can evaluate it. Okay. Now, what does importance sampling do? The problem with this approach is that, so this approach of course assumes that you can sample from P, but it could be that in some regions of your support of your random variables or random vector, you may have very high values of the random vector but very low probability values. In the sense, when you randomly sample, you may not get to that region where there's a very high value of x but low value of probability, and because of which you will miss that sample, because of which your expectation will be completely incorrect, right? So there's an issue with sampling directly from your distribution P if the distribution is not, you don't know how the distribution looks like, okay, where it is providing more probability mass and where it's not providing more probability mass. So that's why importance sampling is a way to kind of fix that by saying, okay, I have this integral, I'm just going to multiply and divide with another function, okay, which is going to be the function of the same argument, which is z. So in this case, q of z. And then I'm just going to think of this new term, which involves 3 terms now. Previously, it was just 1 with a density function here. I'll have 3 terms with a density function here, and I'm going to approximate this integral with 1 by L times the sum over P by Q and P by Q times F of ZL. So this 3 terms here are the same as here, and they're evaluated at ZL points, which are my samples. And there's a 1 by L because I'm not explicitly taking Q of ZL. That's all. Okay. So this is just called an importance weight, and the reason we are doing this is because, as I said, if you don't do this, and if your probability, the original PZ has a low probability mass at regions where there's a high value of X, you will miss that sample. If a high value of X will shift the mean, right? Let's say you had a distribution which was like this, and then some high value here. So let's say your distribution was like this. So this is X. Okay. So this is P of X. So you can see that let's say X is 1000, but the mass here is very low, and X is let's say 100, let's say 10 here. The mass is very high. When you sample, you will never probably get a sample from here. So the mean, for example, if it's 50, you'll get all your samples here and estimate the mean to be whatever 10 or 12 or something, right? So that's the fix for that's the fix that importance sampling is trying to address. So that's the problem. And there's a trick where you may not even need P of in this method as well, you may not know how to evaluate P at a point as well. So in the graphical models, for example, in the undirected graphical model, we always had this additional factor 1 by z, right? 1 by z was actually a summation over all configurations, which is a hard computation. But we can kind of ignore that and still compute, still do importance sampling in a sense. Let's say we can only evaluate the numerator and not the denominator, which is z of p. We don't know the z of p. And even with an approximating or this proposal distribution, right, q, which hopefully puts more mass on this over this region so that I can sample from there. That guy's denominator also I don't know. I can still do importance sampling, except that I'll somehow have to deal with this constants at some other point of time. And here the fix is you can replace the factor zp by zq, which are the partition functions for the p distribution, the q distribution, with the same factors that you had. So p by q at your evaluation at your sampled points, you can just take an average and just call that as a factor. So it's a minor point. All I'm saying is sometimes you have access to drawing a point from a distribution, as in evaluating a point at a distribution. So for example, you can sometimes find P of A. Sometimes you can only find P tilde of A, in the sense you don't know the Z factor. So the log factor, the partition function you may not know. So you can only do P tilde of A, which is just going to be the product of the factors that you had, right? So 1 by Z is not there. So if you get rid of that, then that's P tilde. Is importance sampling clear? Or at least the motivation of why we are doing importance sampling? So rejection sampling and importance sampling are just trying to do better Monte Carlo averaging. Monte Carlo averaging is all about getting some samples, saying that that's the proxy for my expectation or whatever computation you're doing, right? So then we can get to some more advanced methods which actually involve what are called Markov chains. So how many of you have heard of Markov chains? From which, so I've taken a class where they've done Markov chains.
I've used it in just finding probabilities based on transition matrices.
Yes. Okay, so some of you might have done a course on applied probability or statistics in your undergrad or one of your previous classes. So there you might have seen Markov chains. So we'll not go into the theory of Markov chains here. It suffices to say that in the previous two sampling methods, we were sampling from Q, right? Essentially, we are sampling from Q, the points, the L points that we were supposed to sample, XLs, right? When we are sampling from Q, from one sample to the next, they were not related to each other at all, right? They were essentially, I drew a sample from Q, in the next step, again drew a sample from Q. That has nothing, those are independent samples, okay? In fact, they are independent and identically distributed samples, right? Now, this other method, so Markov chain based Monte Carlo methods, they don't create independent samples from one iteration to the next. And the first method that we're going to look at is called Gibbs sampling. So they will create dependent samples, but hopefully their strategy is to create these dependent samples, which after sampling a lot of times, you start getting samples which are actually from the distribution you cared about. So you cared about sampling from P of X, right? X bar. Let's say we care about sampling from P of X1 to X6. Okay. We want a sample from a joint distribution which is represented by this graph. Okay. We want a sample from that, a sample or whatever L samples from that. To get those samples, we're gonna do Gibbs sampling. It's a very simple procedure, but what I'm saying is that it will create dependent samples as a function of a time step. But hopefully, after some number of time steps, it actually generates samples from this precise distribution. Okay. And the idea is as follows. It just samples a sequence of realizations. So see this index, which is at the top. It's a superscript. By superscript, I'm just saying that these are samples. So x0 is actually a 6-dimensional random vector, a realization of a 6-dimensional random vector. X1 is a realization of a 6-dimensional random vector. Okay. Because see, if I draw a sample from this distribution, I actually get a vector which has 6 coordinates, right? At every time step, I get a 6-dimensional vector, 6-dimensional realization. So that 6-dimensional realization, I'm just representing it as x0 with a 0 at the superscript, just to differentiate it from the subscripts which represent our random variables, right? The subscripts represent the random variables themselves. Okay, and the idea is you sample this sequence by updating one variable, as in one coordinate at a time. So what is meant by updating, right? So updating is as follows. We update as in we get a sample, we get a realization of the 4th coordinate by conditioning on a set of by conditioning on all other candidates. Okay. In this case, you just have to, as you saw, maybe not in the directed graphs, but in the undirected graphs, you saw that given the neighborhoods, the random variable is independent of everybody else. So you don't have to condition on everybody else. If this was undirected, if you want to get x4, you only have to condition on the 2 nodes connecting to it, right? So that's the Markov blanket idea, but don't worry about that. Here, because it's a directed graph, you actually have to condition on 3, 5, and 6. Okay, so what exactly is the algorithm? The algorithm is we want to get so the Gibbs sampling algorithm is as follows. If I want to get x1, x2 to x6, okay, I want to get a sample from x1 to x6. So which is one. Let's say this is x0. Okay, this is one sample. I want to get to another sample which is x1. Okay, sorry, x0 and x1, which is another such vector, right? I want to get a sample. Now, how will I do that? I'm going to just fix an order. Let's say, in a sense, let me go from left to right. Okay, I'm going to start with this, and I'll say, okay, let me try to sample p of x1 given x2 to x6 from the 0th iteration. Okay, so whatever are the numbers, I'll fix these numbers. Okay, condition on that, I'm going to sample the first guy. So I'll get x11, or a new sample basically. And then I'm again going to do x2 as the probability of x2 given x11, x30 to x60. Basically, I'm just going to retain whatever was before. I generated this new thing, so I can just use that. I mean, I don't have to use that, but I can use that. I'll generate another conditional distribution. Generate a sample from a single conditional distribution. Okay. So that's the idea of Gibbs sampling. So you just go one variable at a time, one coordinate at a time, and these conditional distributions are easy to compute, which was supposed to be shown by this slide, but let's ignore that. So going from one sample to another sample, let's say if there are 6 dimensions of my random vector, then I'll have to do 6 steps, 6 one-dimensional conditional distributions from which I need to sample. Okay, and these 6 one-dimensional conditional distributions, sampling from them is easy because of this conditional independence property of the graph. Okay, for example, if it was an undirected graph, as I said, given the neighbors, you don't care about everybody else, so the conditional distribution is going to be simple. So that's the idea of Gibbs sampling. Okay. Okay, so yeah, so you can think of, let's say in this case, from the 0th iterate or the 0th sample to the first sample, I took 6 mini steps of 6 one-dimensional conditional distribution samplings, right, to get from 0 to x1. This whole operation can be thought of as one complicated map which says, okay, given the previous lth iterate, generating the l plus 1th iterate. In this case, I'm using 0 and 1, so but you can generalize it to l and l plus 1. Okay, that's the lth sample and the l plus 1 sample. So you can think of it as some complicated way of going from the lth sample to the l plus 1 sample. Clearly, lth sample and l plus 1 sample are not independent, right? And in fact, you can see that this looks like a transition probability function. Just like, so if you know about Markov chains is about if you're in a state, how do you get to the next state? So given the current state, you get to some next state, right? So it's a conditional probability distribution actually, right? So Gibbs sampling, although it consists of many steps, it can be viewed as a transition from one state to another state, and that's where you get into the theory of Markov chains. But you can see that states are dependent because you are actually conditioning on the previous state to get to the next state. Okay, but you can see that after generating, let's say maybe L is 1,000 or 10,000. After 10,000, the samples that you're getting are actually from P of x. And you may ask how? That's because we have actually used P of x, right? We have actually used the conditional distribution. So P of x was the joint distribution from which we wanted to sample. We can't sample from that directly. So we are actually computing the conditional distribution. So P of x is intimately related here. So you'll see that the samples after long enough time are actually drawn from P of x. Okay. So you can now once you this is the art part where you don't know how long enough of time you have to wait. But after long enough of time, you actually get samples from P of x, and then you can do your regular Monte Carlo averaging. Let's say if you're computing expectation, right? So that's the notion of Gibbs sampling. Just the last couple of slides. So, for example, I don't know if you can actually see. Okay, so Gibbs sampling is being graphically drawn here as a curve. So, for example, in this case, let's say we are starting from here, and instead of six coordinates, we have 2 coordinates. Okay. Then for the first coordinate, we are keeping x2 fixed, and so we are making a jump to x1. Right. We are sampling from probability of x1 given x2, and then we are keeping x1 fixed. We are jumping to some other value of x2, keeping x2 fixed, jumping to another value of x1, and so on. So that's what's happening in this Markov chain. So it's like a gridded random walk. Okay, and you can actually see how the jumping happens if you have a 2-dimensional Gaussian distribution. and when you have the same two-dimensional Gaussian distribution, but it is very skewed. Okay. Yeah. So basically, what we are trying to show here is that if you have a very highly correlated random variables, then you don't explore certain parts of the state space. Whereas if it's not correlated, then you explore quite a bit of the state space. I don't know if you can actually see that there is supposed to be a oval or an ellipsoid. Yes, yeah, an ellipsoid is missing here, but there's supposed to be an ellipsoid. It just means that the Gaussian random, the two random, let's say the two coordinates represent Gaussian random variables, they are correlated. Okay. Anyway, so we will stop here. Actually, let me just get to summary. So inference computations on joint distributions is a hard problem if you think about it naively. Like if you think of, as I said, 100 random variables to 2 values per random variable, it's 2 to the power 100 terms in your summation. Instead of that, today's lecture was talking about how to do it efficiently for tree models. Is efficient, in fact, linear time, which is basically the belief propagation algorithm. You can also use variable elimination. That was a primitive algorithm, but there we did not know how to order the summations. And then we also discussed a family of approximation methods based on basically sampling. So we focus a little bit more on Monte Carlo methods, but then we'll talk about Markov chains more maybe in the next class as well. So it will be more clear. Okay, that's it.